Hello, welcome to the Philip J. Currie Dinosaur Museum virtual speaker series, where we have paleontology guests call in for a presentation on science, fossils, and dinosaurs, and where the public will be able to ask questions live on YouTube. First off, we want to acknowledge that we are on the homeland of the many diverse First Nations and Métis people whose ancestors have walked this land since time immemorial. We are grateful to work, live, and learn on the traditional territory of Treaty 8. Today, Michael Hudgins will be presenting his talk titled From Neglected to Appreciated, the Paleobiology and Evolution of Thescelosaurids. Michael is from Yorktown, Virginia, which is 3 hours south of Washington, D.C. Growing up, Michael was captivated about the natural world, including rocks and extinct animals. Although his interest about the natural world wavered throughout life, he ultimately pursued and completed his undergraduate degree in geology at George Mason University in Fairfax, Virginia. Michael then went on to pursue his master's in evolutionary biology at the University of Alberta in Edmonton, supervised by Dr. Corwin Sullivan. He is currently writing his master's thesis on Thescelosaurids from northern and southern Alberta. For those tuning in, you can type your questions in the comment section, and I'll read them to our speaker at the end of the talk. Thank you for joining us today, Michael, and with that, I will let you take it away.
Thank you for that kind introduction. So today we're going to be talking about the paleobiology and the evolution of Thescelosaurids. And I'm going to be briefly talking about some of the new material coming out of the DC bone bed in Wembley, in Grand Prairie, Alberta, just up the street from Philip J. Currie Dinosaur Museum. So most people don't realize that a lot of these dinosaur-dominated ecosystems during the Late Cretaceous period were that there were other organisms that were not gigantic animals, such as like Triceratops and Tyrannosaurus rex, as well as Edmontosaurus. This includes small-bodied ornithischian taxa, which would be made up majority of Thescelosaurid taxa. So a good representation would be Thescelosaurids running around with these gigantic ceratopsid and Tyrannosaurid type animals during the Late Cretaceous period. And so these Thescelosaurid taxa are quite diverse during the Late Cretaceous period, such as Parksosaurus, Orodromius, Thescelosaurus, and Hya. And Joholosaurus may be a little contentious about its placement in Thescelosaurids, as they are their phylogenetics, their evolutionary histories, place them sometimes within Thescelosaurids and sometimes outside of Thescelosaurids. And so the biogeography of Thescelosaurids during the Late Cretaceous, we only recovered a few fossils from, we cover fossils from North America as well as in Asia. So North American taxa are both found in Canada and in the United States. And this includes like Thescelosaurus neglectus, Parksosaurus, Albertodromius, Orodromius, Zephyrosaurus, and Erectodromius. Right. And Asian taxa are represented by Hya, which is found in Mongolia, Changchungsaurus, which is found in Asia, and Joholosaurus, which is a potential thescelosaurid that is found in China, as well as Korea with Krianosaurus. As you see here by this graph, there is the Cretaceous timescale with the oldest at the bottom and the Maastrichtian at the top, which is coinciding with the end of the dinosaurs, which is further closer to the present. And you can see that Canada has specimens here, which is by Thescelosaurus acinoboensis, Thescelosaurus neglectus, Parksosaurus, and the United States with Thescelosaurus neglectus and Orodromius, as well as China specimens, Mongolian specimens, and Korean specimens. And we have two skulls, Thescelosaurus neglectus from North America and Hya from Mongolia, which are representative of a North American taxa and an Asian taxa. So I'm going to talk about the phylogeny of dinosaurs and where Thescelosaurids are placed within Dinosauria. So here is a simplified phylogeny of tetrapod organisms that live on planet Earth. We have amphibians, mammals, lizards and snakes, crocodiles, non-avian dinosaurs, and birds. On the left, we have the geological time scale, with at the bottom, again, is the oldest, and at the top is present day. So dinosaurs are a unique are placed within a unique clade of organisms called Archosauria, which includes crocodilians and as well as birds. And birds are within, as you see, with Dinosauria. So there are avian dinosaurs and the non-avian dinosaurs, which are your Stegosaurus, your Tyrannosaurus rex, your Triceratops, and as well as your Thescelosaurids. And dinosaurs lived within this time period called the Mesozoic. And the Mesozoic is broken down into three sections. You have the Cretaceous, the Jurassic, and the Triassic. And Thescelosaurid taxa are usually found, or mostly found, in the Cretaceous time period, closer to the upper part of the Cretaceous, towards the end of the dinosaurs. So getting a closer resolution of dinosaur phylogeny, dinosaurs can be broken down into two groups. You have Saurischians and then you have Ornithischians. Saurischians can be broken down further into Theropoda and Sauropodomorpha. Theropoda, which includes your Tyrannosaurus rex, your Velociraptor, as well as birds. And sauropodomorphs are your long-necked dinosaurs in the late Jurassic and also in the Cretaceous period, the really gargantuan animals. Ornithischians can be broken down into three groups, which would be Thyreophorians, which are your Stegosaurus and your Ankylosaurids, as well as your ornithopods, are their own group, which we'll be discussing further. This is where Thescelosaurids are thought to be present in, and Edmontosaurus are within ornithopod groups in Ornithopoda. And then lastly, Ornithischian can be broken down into marginal cephalians, which includes your Pachycephalosaurids and your Triceratops. So ornithopods with Thescelosaurids are sometimes placed within ornithopods. Their evolutionary history is fairly contentious. We don't really know exactly where Thescelosaurids belong on the Ornithischian tree, but we have some ideas. But for the sake of this, they are sometimes classified in Ornithopoda, but later on in this talk, we will see that sometimes they are placed outside of Ornithopoda. And thus, I will be calling them fairly basal Ornithischian taxa. And so this leads into what do I mean by basal? And it's not an herb, but basal is the ancestral or primitive condition, and is basically an organism that possesses traits that resemble the common ancestor. And the opposite of ancestral or primitive is derived, which means advanced, and is basically an organism that possesses a trait that was not in the last common ancestor. So, for an example, we have the phylogeny of primates, with humans and gorillas being more derived and monkeys and baboons being more basal. So monkeys have a lot of characteristics that are in common with a common ancestor, that are present within the common ancestor, while gorillas have more derived traits. They don't have a lot of characteristics that are in common with monkeys or the common ancestor. So the systematic history or the taxonomy of Thescelosaurids is fairly complex. And so I'm going to give a very short summary of the taxonomic history of Thescelosaurids for context of this talk. So the first ever small-bodied bipedal plant-eating dinosaur was named and described in 1869 by Thomas Huxley. And he named it Hypsilophodon foxi. And like I said, it was the first ever small-bodied plant-eating bipedal dinosaur that was discovered. Hypsilophodon during this time period was very contentious of where it belonged in the phylogeny of Dinosauria, within the taxonomy of Dinosauria. And there was a lot of heated debate about where Hypsilophodon belonged. It was thought to be belonging at that time, to iguanodons, which are larger bipedal, maybe quadrupedal Ornithischian plant eaters, or it made up its own group, which was argued by Hulk, Owen, and Fox during this time period in the 1800s. But Dolo in 1882 placed Hypsilophodontidae in its own placement. Placed Hypsilophodon in its own placement called Hypsilophodontidae, which is outside of Iguanodontidae, which is the relatives of Iguanodon. Later on, during the 1890s, a fossil was collected from Wyoming that was left touched until until the 1910s, when a man named Charles Gilmore described this specimen in 1913, and he just called it Thescelosaurus neglectus, which means the marvelous neglected lizard, thus the term neglectus. And he described it in 1930 and placed it within Comparative. And Comparative is a late Jurassic, another late Jurassic ornithischian that he thought at the time resembled Camptosaurus. But in 1915, when he uncovered more of the fossil material, he discovered that it did not resemble Camptosaurus really that much, and then thus placed it within Hypsilophodontidae because it resembled closely with Hypsilophodon. So in 1940, Sternberg split Hypsilophodontidae into two subfamilies, which is Thescelosauridae and Hypsilophodontidae, which was further to discriminate the differences between Hypsilophodon and Thescelosaurus, as he discerned that there were many, many differences between the two animals. Within 1974, Galton placed Thescelosaurus within Iguanodontidae based on hind limb proportions. I find this as a weak argument, just basing it on hind limb proportions. But towards the end of the 1900s and late 1900s, 1990s, scientists have discovered that Hypsilophodontidae is an invalid grouping of animals based on phylogenetic analyses. And then later on in the early 2000s, a lot more specimens of these small-bodied ornithischians, these small basal ornithischians from the Cretaceous period, were being recovered. And this led to a much more robust phylogenetic analysis in the early 2010s, thus discovering or trying to figure out if there's a monophyletic group or a unifying grouping of late Cretaceous ornithischians. In 2008, Butler did an analysis of ornithischians in general, and he recovered all the major ornithischian clades, such as marginal cephalians, ornithopods, as well as thyreophorians. But he did not get a very good resolution on Thescelosaurus neglectus and potentially closely related fossil taxa. As you see, there is a large polytomy here of unresolved evolutionary relationships between these taxa. Later on in 2013, Brown and company tried to figure out if there's any relationships with these basal ornithischian taxa. And he did find that there was a monophyletic grouping here in node A, which he called Thescelosauridae, which included Thescelosaurus neglectus, Chain-Chunkosaurus, Joholosaurus, Parksosaurus, Orodromius, and Albertodromius. But he also found that Thescelosauridae can be broken down into two clades. We have Thescelosaurians, which include Thescelosaurus, Chain-Chunkosaurus, and Joholosaurus, as you see here, as well as Orodrominae, which includes Orodromius, Erectodromius, and Albertodromius and their kin. Thescelosauridae and Orodromiae. Thescelosaurians, they have a fairly elongated snout, as you see by this Thescelosaurus sketch, while Orodromians have a very short snout, as you see by this Orodromius sketch. Further on, Boyd 2015 did a much larger phylogenetic analysis, trying to parse together the evolutionary relationships of these basal ornithischians. As he recovered the Thescelosauridae, in which he called Parksosauridae, which recovered Thescelosaurus and Orodromius and Erectodromius within this group, but as well as Thescelosaurians and Orodromians. Orodromians are in blue with Orodromius and Zephyrosaurus and their kin, and Thescelosaurians with Thescelosaurus, Chain-Chunkosaurus, and Haya, and Parksosaurus within that grouping. So we have a late Cretaceous clade of basal ornithischians living alongside these larger ceratopsians and derived hadrosaurids during the late Cretaceous, even though they are basal. And the relationship with Thescelosaurids amongst ornithischian taxa, they are sister to sauropodans, which includes marginal cephalians and ornithopods. So they're not within ornithopods apparently, but there has been some more phylogenetic analysis that needs to be done to have to fully resolve this. But at this point in time, they appear to be sister to sauropods, which includes marginal cephalians and ornithopods. So I'm going to talk about the paleobiology of Thescelosaurids in general. And this is a reconstruction of the dinosaur park formation with all the large mega herbivores, such as Styracosaurus, Chasmosaurus, and Lambeosaurus. But I've noticed in this picture, there wasn't any small-bodied basal ornithischian taxa. So I put it on myself to include these small-bodied ornithischian taxa to complete the picture of the ecosystem during the Campanian of the Cretaceous. So there was a study done by Lyson and Longridge in 2011 that tried to figure out what the preferred environments of these late Cretaceous dinosaurian taxa. So he was looking, this group looked at the Hell Creek Formation and seeing which fossils are more abundant in certain rock types. So let me pull out my laser pointer. So in this graph here, in the y-axis, we have the abundance of fossils, and the gray and the dark boxes are representative of the type of rock. So the black box is a mudstone, and the gray box represents a sandstone. As you see here, ceratopsids are more found or collected more commonly in mudstone deposits as opposed to sandstone deposits, while as hadrosaurids are collected in more sandstone types of deposits. The mudstone dichotomy is interpreted as the abundances are interpreted as like the habitat preference. So the black boxes so ceratopsids are commonly found in mudstone deposits, and this has been interpreted as them preferring floodplains, type of floodplain environment, while hadrosaurs are prefer channelstone deposits and probably live close to the river's edges. And Tyrannosaurus, as you see here, is found in equally both, and this makes a little bit of sense because both their food items are living in both type of environments, so they probably don't have a preference of where they would live because they're following the food. As you see with Thescelosaurus, Thescelosaurus is found predominantly in sandstone deposits as opposed to mudstone deposits, and it's been interpreted that Thescelosaurids probably enjoyed sunny channel side, riverside environments where they frequent the rivers and eat the vegetation along the riverbed. However, the study is still fairly contentious about the preferred environment that these animals lived in. And more studies need to be done to elucidate the ecosystem and the environment preference for these taxa. So the teeth of Thescelosaurids are heterodont, which means they have different types of teeth within their jawline, as opposed to like Edmontosaurus and Triceratops, where it seems that they have pretty consistent dentition throughout their tooth row. And this has been interpreted that they have a wider range of diet. They probably ate a large selection of plants. And I would not doubt that they supplement their diet for protein, such as small lizards or bugs as well, because of their heterodont dentition. So Thescelosaurus has also been interpreted as swift runners based on the ratios between the femur and the tibia. The femur is your upper hind limb bone, and the tibia is your shin bone. And they also have been interpreted as burrowers. Back in 2007, there was a fossil discovery of a thescelosaurid called Eryctodromeus that was recovered in a burrow-like den. And this has been interpreted that these guys or thescelosaurids in general, were probably burrowers living in the den and probably having some form of parental care based on the fossils that were found within that burrow, as there were adults present within the burrow as well as juveniles. And also Erectodromus probably would have been a swift runner based on the femur to tibia ratios. So Thescelosaurids might have been swift runners and probably denned to avoid predators, as well as swiftly running away from them as well. So they have a pretty interesting paleoecology. And we haven't seen burrowing. This is the first instance of a dinosaur being able to burrow. And I don't think we have discovered another dinosaur or outside of Thescelosaurid that would be able to burrow. So the growth stages or the growth of these animals of Thescelosaurids is fairly unknown. And this is called ontogeny. And so not a lot of work of understanding their growth has been conducted. Only a few examples such as Orodromius, as well as Erectodromius, and Thescelosaurus as well, and some of Joholosaurus. But there's only a couple studies looking at bone histology of Thescelosaurids, and bone histology is taking bones and slicing them and taking those really thin slice section, putting them under a microscope and understanding their growth rates and what kind of features they have within their cross section. And so here we have an example of Orodromius of a baby femur, a juvenile femur, and a subadult femur or tibia. So with the baby femur, it's fairly vascularized with a lot of blood vessels. And this is signifying that the animal was growing fairly rapidly and is still a very young animal. There are no lags or lines of arrested growth, which is basically like the tree rings of animals. This signifies how old they are, and there are no lags within this baby femur. So it's suggesting that this animal was still growing and less than a year old. The juvenile femur has less vascularization towards the edge of the bone, as you see here, more vascularized towards the center. And they have one line of arrested growth here. And this signifies that the animal is growing and is older than the baby. It's about 1 year old, but it's slowing down in growth because there's less vascularization present on the animal, suggesting the animal is older but not quite at adult age yet. In the adult femur, subadult femur and tibia has more lines of arrested growth, as you see here, and the vascularization from the inner bone to the outer bone decreases substantially, with the outer bone having less vascularization compared to the inner bone. And the lags for the subadult femur and tibia for Orodromius is roughly between 2 to 3 years old, depending on which element you're looking at and which individual you're looking at. So the maximum age for these animals might be around 3 or 4 years old potentially, but they lived pretty quickly compared to other dinosaurian taxa. So here's a continuation of ontogeny, and this is Joholosaurus. Like I said, might be outside of Thescelosauridae, depending on which phylogenetic analysis that you are looking at. And so we have a juvenile Joholosaurus right here with large eyes, and if you notice, it has a very short snout. And when we look at juvenile specimens, the snout gets larger. And then when you look at the fully adult specimens, the snout gets even more larger. As you see, you have a progression from shorter snout to larger snout as the animal gets older, which is actually quite interesting. So an interesting question about the paleobiology of Thescelosaurids is, what did they look like in real life? What sort of integument do they have? Were they feathered or were they scaly? And here's an example of not a Thescelosaurid, but an animal called in the group Heterodontosaur, which is this is a Jurassic animal called Tian Yulong, and it's a Heterodontosaur, like I said, and it's been interpreted as being fully feathered, and it questions whether or not Thescelosaurids or these basal ornithischian taxa were fully feathered as well or were scaly. So we have a couple of examples. We have Psittacosaurus, which is a basal ceratopsid, and Tian Yulong. which is the heterodontosaur we saw earlier. And as you see over here, that Psittacosaurus on the tail has these bristle-like filament-like structures. Whether they're feathers is up for debate still. And the same thing with Tianyulong, which has these bristle-like feathers or integument on the back of the animal. With this, there has been a discovery called Culanodendromeus, which also has feathered integument or feather-like integument on the body of the animal. These feather-like integuments don't look like the feathers that we see on birds. They're not pennaceous, but they have like these filament-like tufts along the body of the animal. But what also is really cool is that the tail has this, and the tail and the hind limb, the bottom of the hind limb, have these keratinous-like scales along the tail and the hind limb, at the bottom of the hind limb, as you see here, which is kind of fairly interesting, given that Thescelosaurids are fairly closely related to these guys, and they might actually look like this. But this animal would have had fully tufts on its body, a tail that was fully keratinous with scales, and the bottom part of the foot would be keratinous with scales, just like a chicken. But this animal would have been probably the size of a dog, and it looks, the reconstruction looks fairly cute. I would not imagine this animal was still around today that this would be a pet. So this leads to the question whether or not these Thescelosaurid taxa from the late Cretaceous period were also have some form of integument along its body. And we don't have any of that soft tissue integument or skin preservation of Thescelosaurids, so we really don't know what these guys look like in real life. And so you can reconstruct them either way, potentially, either having some form of integument on their body or fully scaled. But we can also look at the phylogeny of these animals, such as Culanodendromeus, Tianyulong, and Psittacosaurus, and where these integuments fall on the family tree, so we can get a pretty good estimation of whether or not these Thescelosaurid taxa will fully feathered or not. So with Psittacosaurus being a marginal cephalian, really closely related to Ceratopsia, and Tianyulong is fairly basal on the Ornithischian tree, and the Culanodendromeus is fairly closely related to Thescelosaurids. I'm sorry, I should have backed up a little bit. So this is a color-coded phylogeny, and scales are in pink or purple. Monofilaments, which were present in Tianyulong and Psittacosaurus, were in red, and the tufts of filaments were in blue for Culanodendromeus. As you see here, that Tianyulong is fairly basal in Ornithischian standards, and Psittacosaurus being closely related to Ceratopsia, late Cretaceous Ceratopsia, and Culanodendromeus is fairly basal to Thescelosaurids and Sauropods as well. So you can interpret Thescelosaurids as having either scaly skin or some type of scale, some type of monofilament or tufts of filaments on its body. But it's really hard to say based on we don't have any of that skin preserved on the body of the animal, of these animals, excuse me. So you can interpret this as, like I said, as being feathered with a body, something similar to Culanodendromeus with the feathers around the body, the tail being keratinous with scales, and the bottom of the feet being keratinous with scales as well. Or you can interpret these guys, these Thescelosaurid taxa, as being fully scaly as well. Until we get skin preservation of Thescelosaurids within the fossil record, it's really up in the air what these guys look like. So in 2000, there was a paper describing a Thescelosaurus from the Hill Creek Formation that was potentially having a heart. This specimen is called the Willow specimen and is now housed in North Carolina State Museum. And the original authors who described the specimen thought this mass in the chest cavity of this Thescelosaurus specimen was a potential fossilized heart. And so the scientists did some CT scans, and what they thought they found were the valves of this supposed heart in Thescelosaurus. But under close examination, there was other types of this morphology around the skeleton of the animal, of Thescelosaurus, that were fairly similar to the composition and morphology of the supposed heart. So this thing at the bottom of the hip is an iron concretion. It's just pure iron. And they did a CT scan and did some composition work, and it has the same morphology as the supposed heart with the iron concretion towards the hip, and it's made of the same material. So it's very likely that this is not a heart, but in actuality it's an iron concretion. So dang it. So further on about their paleobiology, we have potential uncinate processes or structures that are similar in function with uncinate processes. And uncinate processes are typically found in theropod dinosaurs as well as modern day birds that assist in the breathing and respiration of these animals. And so these intercostal plates, which are called in Thescelosaurids, probably pose a similar function to uncinate processes seen in theropods and birds. However, as you see in Parksosaurus here, those are the intercostal plates, and these are the intercostal plates for Thescelosaurus. However, the development of these intercostal plates in Thescelosaurids developed differently from the uncinate processes in birds. And so the uncinate processes in birds ossify from the out to the inward. And with the intercostal plates for Thescelosaurus, they ossify from inward to outward. So a completely different osteogenesis. So segueing out of the paleobiology of Thescelosaurids, we're going to talk about my research up in northern Alberta that's been predominantly my master's thesis. And we've been describing new thescelosaurid material from the DC bone bed up in Grand Prairie, Canada. And this material is fairly important for a number of reasons, which I'll continue in a second. But this material is coming from the Dinosaurian bone bed, or the DC bone bed, like I said. And it's a fairly small quarry along the Wapiti River. And it's quite a terrifying climb down. I am deathly afraid of heights, but the only way to get down to the quarry level is taking these self-made stairs in the cliff face to get down. And when I was there, I was shaking very, very uncomfortably going down, because me and heights are not best friends. But the quarry is pretty cool. It's very muddy and it's very small, but it has a lot of fossil material of Thescelosaurids coming out of this. And so the importance for this fossil material is quite interesting. So here is a stratigraphic columns of northern Alberta, southern Alberta, central southern Alberta, northwestern Montana, as well as thescelosaurid occurrences. And so the way to read this is, here's the time scale right here. Here's the Campanian, then the Maastrichtian. And this line right here represents 70.6 million years ago, and this is 66 million years ago, which represents the age of the end of the dinosaurs. And so anything at the bottom is older, and anything at the top is younger. And all these boxes here represent rock formations. And so the gray represents terrestrial environments, and the dark gray represents marine environments. So in the older Belly River group of Alberta, in southern Alberta and in northwestern Montana, Orodrominae taxa are only found in these older sediments. While in younger strata, in the Horseshoe Canyon Formation and the Schollard Formation, only Thescelosauridae taxa have been discovered so far. And so in between these two stratigraphic units, between the Horseshoe Canyon Formation and the Dinosaur Park Formation, we have this marine interval called the Bear Paw Formation in central southern Alberta, which basically truncates the evolution between Orodrominae taxa to younger Thescelosauridae taxa. So we don't really know if there's a turnover event or if Orodromines become Thescelosaurians. We don't really know. But the DC bone bed appears to be a terrestrial representation of the bear paw formation. So the Wapiti Formation records the entire terrestrial sequence between the Campanian all the way to the Maastrichtian, and thus provides insight about the evolution of Thescelosaurids during this time frame because of the truncation of the bear paw formation, obscuring the Thescelosaurid evolution during that time period in southern Alberta. So I'm trying to figure out what these fossils represent, whether or not that coming from the DC bone bed represent a thescelosaurid, an orodromian or a thescelosauridae, and hopefully elucidate the evolution of this group during the late Cretaceous of North America. So here is a reconstruction of the paleogeography during the bear paw formation times. In Drumheller, at that time frame would be underwater, but Grand Prairie would be terrestrial, and we can get fossils from that time period to understand what is going on during that time period. And so the DC bone bed is in between two dated rock units around 73 million years ago, or it's between 73 million years ago and 72 million years ago, which coincides roughly with the bear paw formation. So the DC bone bed represents that missing time interval between older orodromian taxa and younger thescelosaurian taxa. So for understanding what this material is pretty crucial into understanding what's going on in North America and these basal ornithischian groups during the late Cretaceous period. And so we have a few fossils here of the DC bone bed thescelosaurid. We have the quadrate, which is part of the skull of the animal, the femur, which is the upper hind limb bone of the animal, and we have the fibula and a tooth. The fibula is part of the shin bone. The shin bone makes up two bones, the tibia and the fibula. So the next time you eat a chicken bone, that little splint of bone that you take off from the larger bone of the chicken bone, that is the fibula. So this is the fibula of this potential thescelosaurid. So the tooth from this quarry is fairly similar to Thescelosaurus or Thesselsaurid teeth. The tooth is fairly bulbous, just like Thescelosaurus neglectus, as well as Joholosaurus, and also as well as Changchungsaurus and Haya. But what's unique about this is that it has these vertical ridges running along the tooth itself, fairly similar to Thescelosaurus neglectus, but not really with Joholosaurus or any other Thesselsaurid taxa, especially not Zephyrosaurus or Haya. And so this tooth is fairly similar morphologically, and the features present on this tooth are fairly similar to Thescelosaurus neglectus. And so it appears that it would be a thescelosaurid based on just this tooth right here. And I forget to mention that this tooth was found, is most likely representing the front upper teeth of a thescelosaurid, not the back teeth, but a front premaxillary tooth of this animal. So this element right here is called the quadrate, and the quadrate is found along the skull, the back of the skull, and acts as a hinge joint for the lower jaw. The quadrate from the DC bone bed is quite morphologically similar to Thescelosaurians, but it is smaller than Thescelosaurian quadrates, but it is, however, larger than orodromian quadrates. And morphologically, the DC bone bed is very dissimilar from orodromian quadrates. They have a fairly different morphological features that don't really look like the DC bone bed. But the DC bone bed quadrate looks very, very similar to the quadrate of Thescelosaurians, such as Thescelosaurus neglectus and Changchungsaurus, as well as Haya. The femur is fairly interesting in the DC bone bed. It's got the features of a dinosaur, the fourth trochanter. It's pretty diagnostic of a dinosaur. The fourth trochanter is basically a diagnostic feature, like I said, a dinosauria. but also acts as a main retraction for the femur when in locomotion. I compared the femur with all other thessosaurid taxa as well as other late Cretaceous dinosaurian taxa, but the DC bone bed is very, very similar to other thessosaurid femurs. They're bowed, they're all bowed, as well as the fourth trochanter is rather pendant shape. The fourth trochanter on the DC bone bed is damaged at the distal end, but it would have extended further down based on that damage. So it had a fairly pendant fourth trochanter, just like other thessosaurid taxa. They also have this cleft that separates the lesser trochanter, which is a muscle attachment site for the animal in life, as well as the greater trochanter, which is also another muscle attachment site. That is similar to other thescelosaurs. They have that cleft that separates them out. But what's interesting is that the femur is fairly robust compared to other thescelosaurids, both in width and also the lesser trochanter is fairly large compared to much larger thescelosaurid animals. And so that made me question, is there a way to quantify how robust this femur is compared to other thescelosaurid femora? And so I did a simple ratio of a femur width over femur length to see how robust the animal is, how robust the femur are. And so in the y-axis, we have the ratio here, and in the x-axis is different thessosaurid taxa. And the dotted line separates out thescelosaurians from orodromines. Orodromines are blue, thescelosaurians are red. And Asian taxa are represented by the square, and North American taxa are represented by the circle. And the green is the DC bone bed thessosaurid. As you see here, thescelosaurs are fairly more robust compared to orodromines. The two Joholosaurus are representing a juvenile specimen, and the adult specimen is here. So overall, the thescelosaurian taxa are fairly robust compared to orodromines. But the DC bone bed is more robust than Thescelosaurus neglectus, which is quite astonishing given that it is very small compared to Thescelosaurus neglectus, but it has overall a much more robust morphology compared to other thescelosaurid taxa. So the fibula is pretty typical of a thescelosaurid. They have a lot of morphological features that are in common with it. It doesn't appear to be a ceratopsid or a hadrosaurid, because hadrosaurids and ceratopsid fibulae are fairly robust compared to this. They're just overall more bigger, and it does not look like a pachycephalosaurid based on Stegosaurus, where the fibula is fairly splint-like. It reminds me of a chicken fibula. It's just very small, and it doesn't extend all the way down to the ankle, unlike the fibula of this thesselsaurid and thescelosaurs in general. But when comparing with other thescelosaurid fibula, it looks fairly similar to Thescelosaurus neglectus. So here's the DC bone bed thescelosaurid fibula. Here's Thescelosaurus neglectus, Orodromius fibula, and Joholosaurus. As you see, it looks fairly similar to Thescelosaurus. It has this kink right here that's similar right here. And it has this, Thescelosaurus has a slight sigmoidal shape compared, which is pretty similar to the DC bone bed one, as it has a sigmoidal shape here. So if you follow this, here's the end that is touching the ankle of Thescelosaurus, and it curves up and then almost forms a sigmoidal shape, which is very, very similar to the DC bone bed Thescelosaurid. And so when I was doing the description and the comparative work at the end of it, I was fairly convinced that it was some form of thescelosaurid, whether it was an orodromine or a thescelosaurian. I was not able to discern based on comparative work alone. But when I inputted it into a keratin matrix by Boyd 2015, the DC bone bed thescelosaurid appeared to be fairly close. It appeared to be within Thessalosauridae, but forms a polytomy or an unresolved relationship with other Asian representatives such as Changchungsaurus, as well as Haya. So the features that diagnose the DC bone bed thescelosaurid are features in the quadrate as well as the femur. And it appears that they are fairly closely related to the Asian representatives. And so with this, we can get somewhat of a picture of what's going on during the Late Cretaceous, during the Bear Paw Formation in southern Alberta, as this fossil taxa represents that missing time period in thescelosaurid evolution. As I said earlier, the Orodromine taxa occur in younger sediments in the Dinosaur Park Formation, Old Man Formation, and so forth. And Thescelosaurians occur in younger formations, such as the Horseshoe Canyon Formation and Scholar Formation. And so it appears during the Bear Paw Formation, or during Bear Paw equivalent times in northern Alberta, is that Thescelosaurians were present during this time period. Whether or not that Orodromines evolved into Thescelosaurians, probably unlikely, but the fossil material probably represents an Asian migration into North America of Thescelosaurians potentially. But more fossil material is needed to figure out this problem of thescelosaurid evolution in the Late Cretaceous period, as you see here. So overall, it seems that the material coming out of the DC bone bed is a thescelosaurid, and more closely related to Thescelosaurians, Asian representatives such as Changchungsaurus and Haya, as features present in the quadrate as well as the femur. And as well as the femur is quite robust compared to other Thescelosaurid taxa, as it has the most robust features, femur width over femur length of any Thescelosaurid. And so with this, Thescelosaurid evolution and Thescelosaurid research is pretty important because these animals represent kind of a hidden diversity during the Late Cretaceous period, in which they probably make up a large percent of the ecosystem during that time period because they are small-bodied, but we really don't know much about their evolution, or nor do we know about their paleobiology. We don't really know much about their morphology, their individual variation between different individuals. We don't really know about their ontogeny, and let alone we don't really know about their evolutionary relationships amongst Ornithischia in general. So with this, the DC bone bed is a fairly important find for Thescelosaurid evolution and paleobiology because it represents a Thescelosaurid in a time period that has not been documented or been described, and we really didn't know much about this group of animals during this time period, and this fossil specimen elucidates the evolution and paleobiology of this group. So here is Parksosaurus taking a bow, and I want to thank my research sponsors, as well as people who have helped me with this project throughout my master's school. And so I want to thank Corin Sullivan and Phil Currie for this project and being inspirations, and as well as the grants from the Grand Prairie Regional College, as well as an endowment from the Philip J. Currie Professorship at the University of Alberta, and as well as the Dinosaur Research Institute student grant for allowing me to travel in weird times to look at specimens. At this point in time, I can take any questions, and thank you for having me.
Thank you, Michael. That was a great talk. So yes, we are going to move into the question period. If anyone has any questions, just type them in the chat. Our first question, what is your favorite dinosaur?
Oh, I can guess and give the cliche answer. I like Tyrannosaurus Rex, but Thescelosaurids have been growing on me, so I really like Thescelosaurus neglectus at this point in time. So I would have to say Thescelosaurus.
Of course. It's a great dinosaur, as you just showed us.
Yes.
All right, second question. What has been the best advice you've been given in paleontology, and who gave you the advice?
Oh man. Well, I'm kind of put on the spot for this one. I don't know.
I guess do you have any advice you'd like to give to somebody looking to paleo?
And getting into paleo, never give up your passions and always be curious about the world. I think that's one of the best advice I can give, because a lot of paleontologists, from my experience and what I've done, it's like we never really grew up. We still like dinosaurs, and so I still like dinosaurs, and never lose that intuition and that curiosity about the natural world, and find your passion. I guess that's the best advice I can give at this point in time.
Beautiful. All right, next question. Are there any features in Thessalosaur skeleton that indicate that it burrowed?
So with Orodromius, and well, Orodromians in general, in previous studies from Verricchio et al. And I think one of his students, Ferron, and he was the advisor, they were looking at morphological features within or Oryctodromius that could be diagnostic to a burrowing behavior. And they found that the scapula was fairly different from other Thescelosaurids as well as from other ornithischian dinosaurs. And morphological features that would signify a burrowing type of lifestyle would be larger muscle attachments on the scapula. This was called the scapular spine, just for one example. And they linked that as a key characteristic of a burrowing type of animal, is having that scapular spine. So yeah, that was one morphological feature, but yes.
Very interesting. Next question, regarding the Asian migration from Thescelosaurids to North America, is there many specimens found in Alaska?
Only teeth. We haven't found any from Alaska yet. It's from the Prince Creek Formation, I believe. Either Prince Creek or Prince William. I think it's Prince Creek Formation. And we only found teeth. There has been a potential, it looks like there's a Thesaurus in the Prince Creek Formation, but also a potential Parksosaurus. And this is all, I think, Maastrichtian in age. But the Parksosaurus tooth taxa might be up for debate, because the tooth that was found in the Prince Creek Formation was a premaxillary tooth. And we don't have any premaxillary teeth of in the holotype of Parksosaurus. So when the researchers were describing the tooth, it looked fairly similar to Thescelosaurus, but not quite like Thescelosaurus. And so they kind of hypothesized or predicted that the tooth represents a Parksosaurus instead of a Thescelosaurus. But we don't really have a lot of fossils from Alaska that represents a Thesselsaurid.
Well, I guess anybody doing paleontology in Alaska, keep your eyes open. Right. Your undergrad work, was it in biology or geology?
So I got my undergrad in geology at George Mason. And so with paleontology, it can go either way. You can either go in the biological route or the geological route. I went the geological route. Wanted to get that time context of it and understand where these fossils are coming from in the rock and interpreting what the rock tells you about the taxonomy or the environment which these animals lived in. Right. And so I got my geology degree, but it was concentrating in paleontology. So I took a lot of upper level division of biology classes that coincided with my geological studies.
Next question. Will the DC bonebed Thescelosaurus get a new name since it can be diagnosed?
I don't think so. One, because the material is fairly fragmentary and unassociated, as well as there aren't really any diagnostic features within this material other than the fact that the material, the femur is fairly robust, but I don't think it's good enough to name it a new taxa. But it is interesting, and there might be a new Thesselsaurid in the Wapiti Formation during that time frame, but more fossil material that have the diagnostic features that can be compared with other Thesselsaurid taxa across the world need to be found to make that argument.
Next question: has there been any ichnofossils preserving burrows, possibly from Thescelosaurids?
There was in the Verricchio et al., as I mentioned earlier, with the Oryctodromius, there was a fairly large burrow that was corkscrew in shaped, and they found only Oryctodromius skeletons within that corkscrew shaped burrow-like structure in the rock. And so they found adult specimens as well as juvenile specimens in the burrow. And so that what made researchers think, oh, this animal might have burrowed, and it also probably took care of its young in the burrow as well, based on the fossils that were present within the structure. So yes, there are ichnofossils for burrow structures, especially, I think it's only in Eryctodrome, yes.
On a related note, what is your dream fossil to discover?
Ooh, a Thescelosaurid type fossil that's sitting on a nest with a complete ontogenetic sequence, a complete growth series, so we can understand their nesting behaviors and their morphology, their variation throughout their life. I think that would be an ideal fossil, but that's very unrealistic.
You can always keep your fingers crossed.
Yep.
Where have you done fieldwork, and where would you like to do new fieldwork?
For the most part, it's been mostly in Alberta, mostly northern Alberta, but I've done field work in Yorktown, Virginia as well, and also in southern Virginia. When I was in undergrad, I was invited along to excavate a American mastodon down in Yorktown, Virginia, which is kind of funny that it was about a mile away from my house in Yorktown at that time. And so I was invited by one of my geology professors, and he took me along and uncovered a mastodon. So I thought that was pretty cool. But most of the fieldwork was in Virginia and northern Alberta. But I would really like to go to Mongolia. I really, really want to go to Mongolia to do some fossil collecting, and also going to the collections at the museum in the capital, Mongolia, to look at some specimens. So Mongolia is my preferred choice right now.
That would be very amazing. If you had your choice to research any topic in the future, what would it be?
The main problem with me deciding what research topic is, like, I can never, like, I try to, like, I dip my toes into everything. And right now I've been really focused on Thescelosaurids, but I would not mind doing atmospheric reconstructions of either in the Mesozoic or any part of the geological timescale, and trying to relate to any sort of macroevolutionary patterns in the fossil record. But I have a really strong interest in a lot of Triassic organisms. I think the Triassic period has been a very, very interesting time period for fossil taxa, because the body plans and the evolution during that time period is pretty wonky.
Another question here. So are Thescelosaurians and Orodromurines more closely related to hadrosaurs or thyrophorans?
Based on, well, it depends on which phylogenetic analysis you're looking at. Based on Boyd 2015, it appears that they are more closely related to sauropods than they are to thyrophorians. And so sauropods it's basically both ceratopsians and both ceratopsians, pachycephalosaurids, and hadrosaurids. They're more closely related to sauropods than they are to thyrophorians.
All right, last question for you. What's next for you?
Ooh, I'm finishing up my thesis at the moment. I've been looking for PhD programs. I have been accepted to a few, but we have to wait and see where the wind blows me at this point. But it's going to be more school, and just looking for the right PhD school for me.
Great, thank you, Michael. That concludes our question period. For those watching, join us again Saturday, March 13th at 3 p.m. for a presentation by Nathan Enriquez on tracking dinosaurs in the Grand Prairie area and the paleontological significance of dinosaur footprints. Thanks again, Michael, and thank you to everybody for joining in.